You are given two sorted integer arrays and an integer k, form pairs by taking one value from each array. Find the k pairs whose sums are smallest. In the example, nums1 is 1, 7, 11 and nums2 is 2, 4, 6 with k equal to 3. The three smallest sums come from pairing 1 with 2, 1 with 4, and 1 with 6. Because our two input arrays are sorted, we can organize every possible pair into a structured 2D matrix. Rows track elements from the first array, and columns track elements from the second. Values swell as we move downward or rightward, so the global minimum is guaranteed at the top left corner. To find the k smallest sums efficiently without calculating the entire matrix, we seed our system with an initial candidate border. We take the first element of every row and pair it with the absolute beginning of our columns. By pushing these starting boundaries into a min heap, we ensure that every potential row pathway is accounted for, with our smallest value waiting at the very top. Now, we begin a simple loop. We pop the smallest element from our heap and commit it to our final answer. But the moment we extract a pair from a specific row, we must immediately explore that exact path further. We uncover the next candidate directly to its right, and push that new sum back into our heap frontier. We repeat this pop and explore rhythm exactly k times. The min heap dynamically acts as a smart sorting boundary, preventing us from ever inspecting unnecessary, massive values deep in the bottom right of our grid. By only advancing our boundary headers as needed, we harvest our k smallest pairs using minimal step tracking. We begin by setting up our core tracking data structures. We initialize a min priority queue to act as our frontier. Then, we run a localized loop to seed our heap with the first column of our grid layout. This pairs the first element of every row with the absolute starting column header, establishing our starting baseline. Now we enter our primary collection loop, which will run exactly k times. In each iteration, we pop the absolute smallest sum element sitting at the root of our heap. We extract its tracked matrix indexes, reconstruct the original pair elements from our input arrays, and commit them directly to our final results list. The moment we pop a pair from the heap, we must expand our search frontier along that specific row. We check if there is a neighboring element remaining to its immediate right. If there is, we calculate its new sum, capture its tracking coordinates, and push it right back into the heap to maintain our active search boundary. We repeat this precise pop and advance sequence until we have successfully harvested our k smallest pairs or entirely exhausted our matrix options. Because the min heap continuously forces the next globally minimal candidate to the surface, we confidently return our result array, completely bypassing the need to ever evaluate the massive values hidden deeper in the grid. Let m be the length of nums1, n the length of nums2, and k the number of pairs we need. Time is O of k log k. We perform at most k pops and k pushes on a min heap whose size stays O of k, and each heap step costs O of log k. That beats materializing the full m by n cross grid. Space is O of k for the heap frontier plus the k stored pairs in the result. Define the routine that returns the k smallest cross pairs by sum. Start with an empty min priority queue for frontier candidates. Prepare an empty list to collect the answer pairs. Loop over the first column, at most min of k and the length of nums1 rows. Seed the heap with each row start paired with column 0 and its sum. Repeat while we still need pairs and the heap still has candidates. Extract the globally smallest sum together with its row and column indexes. Record the actual pair values from nums1 and nums2 into the result list. If a right neighbor exists in the same row, we can advance that wave front. Push the next cell to the right with its updated sum and coordinates. Return the compiled list of k smallest pairs.